Day 28, Honors Physics, Projectiles, problem number 12. So once again, you will be drawing your diagram. Here's the diagram. You have a ball that's rolling off a table in this direction. Well, it's rolling across the table, so we're assuming the table's flat. It does say level surface. And it's coming off the table in this direction. But it's not going to keep going in that direction. Once it comes off the table, it will then become a projectile in free fall. It will follow this dashed path, half a parabola, so to speak, from location A to location B. And once again, I've looked. These are really the only two obvious starting and stopping points for this problem. You label your point A, where you're starting, and then point B, it lands down here. Now, when it lands down here, it'll still be moving sideways with this horizontal component of 1.5 meters per second. That's the launch velocity sideways, and that stays constant. That's what a projectile does. The independent motion horizontally stays constant. The vertical velocity will be some unknown right now. That's what we're looking for, this v sub y, the final vertical velocity when it strikes the floor. That's one of the two things. Actually, we actually have half the problem done already. It says, the question says, what are the horizontal and vertical components of its velocity just before it strikes the floor, or as it strikes the floor? Well, this is half the answer. This is the horizontal velocity of impact. It's going that fast horizontally when it hits the floor. That's half your answer. So, after you've drawn these diagrams and established A and B, you set up your two columns for your horizontal and vertical motions. Horizontally here, we're not going to be doing much with this. I'll talk about that more in a little bit, but it's good practice to write that in there. This 1.5 meters per second goes into the horizontal column for its horizontal velocity. So here are the tricky parts for first-timers. The initial vertical velocity is 0. The ball is coming off the table horizontally. It's not moving down yet. It starts off with a 0 vertical velocity. It's like you're dropping something vertically. All right, so that's a key problem. And when you have a 0 here, that's kind of nice, but it's not moving vertically when it comes off the table. So the temptation is to put a 1.5 there. No, that's a 0 meters per second vertical motion at that instant. It'll start picking up at a rate of negative 9.8 meters per second squared, as it always does for a projectile in a gravitational field. The other key here is that it's going to fall 3 meters. The vertical component, vertical portion of the motion is going to be a negative 3 meters. It's going to fall 3 meters. And that was given in the problem. I made it 2 sig figs. You can make it even 3 sig figs here. But negative 3 meters. The negative is important. So now we have 3 things in this column. So what we're most interested in is this v sub f right here. And I think you can directly get that from this equation down here, which is our fourth uniform acceleration equation, the v sub f squared equals v sub I squared plus 2as. You plug in your 3 knowns, and you will come out with your v sub f. One note of that, though, at the very end, the last step, it'll say like v sub f equals the square root of some number. Well, mathematically, what you really should put there is v sub f equals plus or minus the square root of that particular number. And you take the negative square root because the final velocity is going to be negative. It's going down, the vertical component at least. Now, a couple other things of note here that could have been asked. This problem could ask, it didn't, but it could ask, what is the range? What is your s sub x, so to speak, right here, s sub x? Well, you could do that now. And the way you would do that is you would solve for t over here, get the time, and then using one of the other 4 uniform acceleration equations, plug that in over here to get your s sub x using v equals s over t. It could also ask you, what is the actual overall impact, the actual impact and the angle of impact of the ball bearing when it hits the ground? In that case, you would take the 2 components that you just calculated. Well, this one you know is 1.5. Then you have your v sub y, that's v sub f, in the y direction right here, and you would put them together and find the resultant. The resultant would look something like this. The angle would be something like this. So that would be your vector that to be looking for. The actual impact speed would be that r. You'd find that by the Pythagorean theorem, and you could use trigonometry to figure out the angle of impact. So those are some extra questions you could have been asked about this problem.